Log on, tune in, find out. Another good idea from Cambridge.
Without further ado, welcome to the last but certainly not least, only least in size, session at this workshop. Chrysoula Tsogka from beautiful Heraklion will talk about, you can read the title.
Thank you, and thank you for the invitation. So I will talk about adaptive time frequency detection and filtering for imaging in strongly heterogeneous background media. And this is joint work with Liana Borcea, who is here, and George Papanikolaou. Now, as I said, the problem that we want to solve is to be able to image scatterers, compactly supported reflectors that are buried in a strongly backscattering medium, and we will see what I mean by that. Now, why this is difficult? It's because the echoes from the reflector that we wish to image are overwhelmed by the field that is scattered by the background medium. And the idea that I want to pursue here is to filter the data prior to imaging in order to remove this unwanted backscattered field. So here is our setup. We dispose of an array. This array is composed by transducers that can play the role of emitters and receivers at the same time. And from each element of this array, we will emit a pulse, f of t, in the time domain. This will create a wave. The wave will propagate into the medium. It will interact with the background medium and the scatterers. And then we will record at all receivers XR on the array the response. Okay, so here I will assume acoustic wave propagation. So what we record on the array is the acoustic pressure field. So this is called the array response matrix. XS is the source position, and for one source position what we record is one column of this matrix. And then we repeat this experiment for another source position, and at the end we have an n by n matrix, which is the n is the dimension of the how many sensors we have, and t is time. Okay. So I don't have to go there. Now, as I said, we assume that the phenomena are described by the scalar acoustic wave equation, which I will recall, but I'm sure that everybody knows here. And we use the following model for the velocity. So V, the velocity of the sound in this medium, is like that. So we have a smooth part, C of x. This smooth part, we assume that we know it. So in this talk, I will assume I know it, but in some other works, we can estimate it. Also, either you know it or you estimate it, but it is important that it is smooth. On top of it, we have some fluctuations, and this is the part of the background that we don't know, and we believe that it cannot be estimated. That's why we model it by a random process mu. Here everything is two-dimensional, but it can be carried out in 3D. And now, so this process varies on the scale Lx in the x direction and Lz in the z direction. And sigma, so typically we call that the correlation length of the medium. And sigma is the strength of the fluctuations. Now, nu here is the reflectivity of the object that I really want to find. Okay. So let me show you here an example of why this model makes sense in real life applications. So this is an example of wave speed, so what is the velocity of the pressure waves in the earth, and this was measured by drilling a hole in the earth, okay, and taking measurements. So you see, I mean, everybody's eyes can see that there is a smooth part, constant at the beginning, and then the velocity increases with depth. And so this is the part that we assume that we can estimate. And on top of it, we have these fluctuations. So these fluctuations, it's not possible to know them or to estimate them unless you make a hole, right? Or you have a perfect idea of what your material is. So this is what we model as a random process. And we assume, for example, that we know the correlation length, the scale on which this fluctuates, the correlation function, and the strength. Okay, so I don't do experiments, I mean real experiments, I do numerical experiments. So here are two cluttered media that are synthetically realized on the computer. this is, I call it an isotropic random medium, because in this case the scale of the size of the fluctuations is the same in x and in z. Like this is isotropic, the fluctuations do not depend on direction. While in the layered case, this is the completely anisotropic case, right? Everything is constant in the x direction, and it depends only with depth. So typically, the array will sit on the top of the medium, let's say, and I will call this direction, which is parallel to the array, the cross range, and the other direction, which is the direction of propagation, I will call it the range. And here we have the strength of the fluctuations is of the order of 10%. Let's say if we have a mean speed, so my background, the smooth part of the velocity in my case will be very simple. It will be just a constant. Now, if the constant is 1.5 kilometers per second, then here I have fluctuations from 1 to 1.9, about to give you an idea of what kind of fluctuations we have. Now, this would be a good example for imaging in concrete, if you try to find cracks or things like that, and this could be an example of imaging in the earth. Okay, this is a good model. Now, here is the correlation function I used to generate this media. Now, so how do we model the data? As I said, we use the model here is the acoustic wave equation. I wrote it as a first order system of equations. It's linear. P is the pressure field, so this is what we record on the array, and V is the velocity, the time derivative of the displacement, and V, this small v here is I use here the model for the velocity that I had in the previous slide. Now rho, the density of the material is assumed to be constant in what I do. So we solve numerically the two-dimensional wave equation in this medium, and I didn't say, but there is a scatterer, so this is the object that we wish to find, and here it will be a small scatterer, and the conditions on the scatterer are the pressure release conditions. This is called an acoustic soft scatterer. Now, because in practice, in the experiments, what we do is that we look only in a part of the material, but the material is bigger, we need to model wave propagation in an infinite domain. And this is done numerically with something that is called the perfectly matched layer model. So it models wave propagation at infinity. It doesn't allow reflections to come back to the computational domain. Okay, so let's see at some data. So first, this is what the geophysicians call traces. So how do we, what is this? Basically, I will show you traces for the central source. So I send a pulse from the central source. It goes into the medium, and then I record on all these elements. And we are looking, here it is rotated, I'm sorry, and here is receiver location, right? And this is time. So basically, you see a hyperbola, because the pulse has it has a shape. It's not just a delta function, it has some shape here. But basically, in the homogeneous medium, what you have on the array is, okay, first you will have the direct arrival, but this is not seen, it's for very small times. And then you will hear nothing, because there is nothing in the medium. The wave just goes away. And then at some time it will interact with this object, and the reflection will come back to the array. So this is exactly what is shown here. Basically, you see nothing, 0, 0, 0, and at some time you will hear a blip. And this is the reflection that comes back, and this time of arrival, it just corresponds to the time that the wave needs to go from the source down to this point and back to the receiver. Okay, so this is what happens in a homogeneous medium, and this is just a homogeneous medium. And if you take this data, I bet you can use any method you want, you can find the location from where this reflection came. Now, if you put, however, your point not in a homogeneous medium, but in this heavy cluttered medium, then this is what you get on the array. You see, this is what I call completely incoherent data in some sense, because I don't see, at least with my eyes, I don't see anywhere this coherent echo, right? And this is what we see in the isotropic clutter, and this is in the layered case. So in the layered case, you can say that this comes from a layered medium because it's obvious from the response. Okay, but there is no way to say, looking at this data, if there is a scatterer in there or not. So we have to do something. Now let's look at the image. So this was the generation of the data. Now we can look at how do we generate an image. And I will use the simplest possible imaging function. So I take a search domain that is around my object, and then I discretize it. So I have points y that run in this search domain. And for each point y in the search domain, I will compute the travel time that it takes to the wave to go from the source down to this point and back to the receiver. And I call it the coherent travel time because here I compute the travel time in the smooth known part of the background. Okay, here my background is very simple, so travel time is just distance over at a constant velocity. Okay, so and then I do what? I evaluate my data, my traces at this travel time, and I sum over all the sources and receivers. And this is what I get in a homogeneous medium. So a very good image, right? The red spot is right on the target, so I know where this object is located. Now, why is this working? Like a very simple explanation is that this locus of travel times is a hyperbola, right? And this hyperbola will sit on zeros in the data, because if I take a point far from this point, then I will get some travel time that is down here, and then the data are zero, so I add zeros, and I will get 0 in the image. Only if I am in the support of that, so very close to my true point, I will get a non-zero value. Okay. Now, what happens when the data look noisy? Of course, you put some curve here and you add the data along this line, you get, either 0, if there is some cancellation, you can get a big or a small value. But however, there is no way you can image this small object here. And of course, it is similar in the layered case. So in the layered case, you can image probably the strongest of the layer. Okay, you can see, but here, look, you have a blip. So it's true, because of some cancellation in this particular example, I see something at a correct location. But this is, accidents can happen. If you move your point a little bit, or if you move your source, this nice cancellation disappears, and then you cannot see it anymore. Okay, so what can we do to improve that? I don't know if you were here last week, but Liliana Boccia talked about coherent interferometry, and I will briefly recall what this method is. So to do that, let me rewrite what I called Kirchhoff migration. This is called Kirchhoff migration or travel time migration, or it might have other names for in other, I think in non-destructive testing they call it A-line or B-line, so everybody calls it something else. But this method can be written in an equivalent way in the frequency domain, and this is what people usually do in order to analyze the method. Okay, so how do we do that? Instead of looking at P in the time domain, we take the Fourier transform. So P hat is a Fourier transform of P from time to omega. And then instead of evaluating at this coherent travel time, I just integrate over omega and I multiply by exponential minus I omega the same travel time. So it's exactly the same thing. Now this is an interpretation, we call it the back propagation. So basically you take your data and you back propagate it in the medium, but how do you back propagate? With this thing, which is basically just the phase of the Green's function in the background medium. Okay, this is what I have written here. We have an estimate of the Green's function in the background medium in the smooth part, and I just use the phase of this Green's function. And so a lot of analysis of this migration method is based on this formula using theory, microlocal analysis and FIOs, etc. So I don't have a reference here, but I could name, for example, Bill Symes or Martin de Hoop, and also Jérôme Lerousseau before doing Calderman estimates. He was working on that. Okay, so now this is Kirchhoff migration. So what do we do in coherent interferometry? Basically, instead of back propagating this P, which is the data, we consider cross correlations of the data over appropriate space frequency windows. Why do we do that? because it is basically a smoothing of the data. So I wrote, it looks ugly, but it's nothing difficult. So here you take p hat, this is the data, and this is again the data. Cross-correlate means I take a conjugate on one side, and I take nearby receivers xr prime, nearby sources xs prime, and nearby frequencies. And then I backpropagate these two guys. How I backpropagate? Exactly the same way as before. So this guy goes with the first one, and the second one goes with a conjugate. That's why I have a plus. And now this story that I said I take only nearby, I have these window functions phi and psi that limit this into to have support in omega d. So omega d is the decoherence frequency. I will only consider correlations of data that are correlated. So I only correlate things that are nearby in frequency and things that are nearby in space. So xd of omega is what we call the decoherence length, and this decoherence length is not constant, it depends on frequency, and this is physical. Basically it's proportional to the wavelength, and the wavelength changes with frequency. Okay, so we just migrate these cross correlations, and why is this better? Basically, if your windows are big, right, if you don't do any smoothing, then you just get the unstable results that you had before, because the cross correlations is just the square of the previous function. Now if they are very small, if these windows are very small, you get stability, but you lose resolution. So in fact there is an optimal trade-off as far as the image is concerned between stability and resolution, and these parameters can be determined so as to achieve this optimal trade-off. Okay, so I have here some references, maybe Liliana showed them. This is the first paper where some ideas about SINT appeared, but truly coherent interferometry was explained in this paper and the analysis was done. The adaptive estimation of the parameters omega d and xd is done in this paper, and the stability, so this is something that I did not say. What is important is the stability. So what do we mean by stability? We mean that this image, the imaging functional, should not depend on the realization of the random medium. So we should see something that is stable. Okay, and we have two more recent papers. I think that Liliana talked to you about this one. Okay, so let me show you an example that this works, although in my case now it will not work. And this is the data. So if you remember, before my data, the sigma was of the order of 10%, and in this case I couldn't see any coherent wavefront. Now I cheat a little bit. I show you an example where sigma is less, and now I can see a wavefront. Okay, here it is. And in this case, this is the image that I get by the standard migration, and if we do this smoothing, we get something better, in the sense that I only have red spots only where the targets are, and my image is stable with respect to the realization. This is not shown here. You have to do more realizations and observe that the results are indeed stable. Okay, so it works when the fluctuations are not too strong. And now if I go to the case of the 10%, of course it does not work, because here I don't have a stability issue only. I have a problem with SNR. So as I said at the beginning, the signal from the object that I wish to image is lost into noise. So a little bit of smoothing will not undo the thing. So we have to work a little bit harder. And the same is true in the layered case. You see that basically all you can see is the first layers in your medium. So we really have to work harder. Okay, so what do? We will look at our data in another way. So we will decompose the data and we will look at them in using some space-time decomposition. We want to look them in another way. So to do this local time frequency windowing, I will use here the local cosine transform, and I recall what it is. So I take each element of my response matrix, and I do the local cosine transform. So these are the traces that we have seen before. And I will construct a tree. At level 0 of this tree, I just do the cosine transform in the whole window. So there is nothing local for the moment. At level 1 in the tree, I will compute the local cosine transform in each of these windows. At level 2, I will cut in 4 windows, level 3, 8 windows, etc. So this way, I'm creating a tree. Here is the tree structure, okay? And in each node of this tree, what I have is I replace my initial data by the cosine coefficients of the data in the corresponding window. And the cosine coefficients are computed as projection onto these spaces. So I have the cosine functions, and chi are smooth windows, okay, in order to cut the data without introducing oscillations. And now what is important is that the union of these spaces over J, so if I fix the level and I take the union of the spaces, then I have an orthonormal basis of L2, and this is important because it means that we don't lose any information while doing this decomposition. Okay, so as I said, at each node in the tree, we now have basically another matrix, which is n by n, but now depends on frequency. And it is the cosine coefficients of the data that depend on frequency. And I want to look at the singular value decomposition of these matrices. So let's look at them. In fact, I will look at normalized singular values as a function of frequency. And let's look at the beginning. So this is the first node of the tree. I plotted 10 first singular values normalized as a function of frequency. So you see that there is nothing to see here, okay? Basically, the only thing that there is to see that all these guys look clustered together. There is no sign of any target or anything. So let's go to another level. So now I go down to this tree at level 3, and I will look at some of the windows. I will spare you, I won't show all, but I will show you a lot. Okay, so this is window number 1, corresponds to this data here. Okay, I still see nothing, okay? All the singular values are clustered together. So I really want you to focus your eyes on this part of the picture, on the first 5 hertz. Okay, so this is window number 3. Again, everything looks clustered together. And now, window number 5, you're supposed to say that you see something different. Do you? Yes? So here something is going on. So they are not clustered together anymore. So was this an accident? I don't know. Window number 7, again everything clusters together. Okay, so the question is this an accident? Because I know that the data, in fact my target was in window number 5, so I win. So let's go to the next level. What is going on? We go to the next level. So this was the good window. So now I'm going to show you only good windows. So you are supposed to see that these singular values are not clustered together anymore, at least in the lower part of the spectrum. And so in window 11, again, I think it's clear that there is at least one singular value that is separated from the rest. And this is another good window. I go down in the tree, okay? And I always choose the window that contains the coherent echoes. And this is the last window that I can go down in my refinement, and I want you to remember this singular value. So it goes from 1 down like that, okay? So it's not an accident. It appears that consistently the window that contains the object, I mean the echoes from the object that I want to find, has this property. So how do we make out of this observation an algorithm? We said, okay, so choose a frequency band of interest. Obviously, for us, the frequency band of interest is this lower part of the spectrum, and a number of singular values to work with. So here I will work with these first 10 singular values. And then we formed this we looked at normalized singular values. So basically, I will form a matrix that contains what you see on this picture. So each column of the matrix is one of these lines, okay? Now, if all the singular values are clustered together, then this matrix means that it is rank 1 because all these vectors are aligned, okay? But when we see something that goes different, this means that we will have a significant second direction. So this is like a pattern recognition, and I seek basically to maximize the ratio between the second and the first singular value of this SVD of the SVD of my initial matrix. Okay? So this is my criterion. So let's see how this criterion performs. I can plot this criterion for each level in the tree and see if this criterion picks the good window. Now this is what we did, and here we have that it does pick the good window. Of course, here we have a ghost, and I will tell you what we do about it. And then it has a clear maximum. So of course, the theory, there's no theory to tell you that there is this is a global maximum. And the only thing I can say that we can use at least some intelligence if we have a priori information. So here I suppose that I have a target that is not moving. Okay, so this guy was there and it was sitting while I was doing the measurements. So this means that if at one level it is in this window, then when I go down in the tree, I can only detect him only in some children of this window. It cannot jump to another window, right? So this is what we use in order to eliminate false positives like this one. Okay, so I think this is a good one. In fact, this is a false. Okay, so now what do we do? So we found a good window with this criterion, and then what do? We say, okay, but if you found a window that contains the information from the object that you want to image, then keep only data in this window. And this is what we do. So we forget all the other data, we put them to 0, and we only keep the good frequencies, the frequencies that permitted us to detect the presence of the object. So this is the first part of the filtering. And we do an additional filtering which says, okay, but you detected this window based on the fact that there was one singular value or two or some singular values that had some peculiar behavior. So project the data onto the space that is generated by the singular vectors that correspond to these singular values, right? Because this is what permits you to detect the object. Okay, so this is the second part of the filter. Now, here I show you the initial data in the layered case, and this is the final data after applying both filters. Of course, the image at the beginning, it was this bad image, and the final image, it's perfect. But I bet that if you take this clean data, and you can use whatever method you want, you can image very well your object. And so this was just Kirchhoff migration, and this is coherent interferometry. And now let me show you how this performs step by step by going down level by level in the tree. So this is the first part of the filtering that selects only the window and projects on the lower frequencies. So this filter only permits us, right, to locate the object better and better in range. So range is the distance, I mean the direction that is far from the array. So we focus better and better in this direction. But it's the second projection that uses the singular, I mean the space that corresponds to the singular value that permits you to locate in the other direction. So it's a combination of the two filters that gives you the final result. And the algorithm that I just presented is in this paper that is to appear. So now everything I showed you was for the layered case. So now nowhere in the algorithm I used the fact that the medium was layered. And of course you can apply this algorithm in other types of random media. So here is an example that I call it the combined, because this medium is a combination of an isotropic one and a layered. I think you can see both the straight lines and the small features. So this is initial data, and this is final data exactly for the same location of the object and the array. And this is the initial image, very noisy, and this is the final image which locates the object. So this was migration, this is sin, but as I said, I think that you can use any method you want and it will work after you filter the data so well. Now, yes, I want to show this example. Now, looking at this data, they look completely random. So I could say, okay, let's take just some data in a homogeneous medium and then add noise to them. What kind of noise? Well, we can add random or correlated entries to the response matrix. And this is what we get. So how much noise did I add it here in order to get a picture that looked similar to me? I added this SNR minus 10 dB means that the power of the noise, power is L2 norm, the power of the noise is 100 times the power of the signal. So this is really lots of noise. And then you say, okay, let's do an imaging. What will happen? Any guess? Well, this will happen, okay? This image is perfect. It doesn't matter that you put all this noise in the data, because in the imaging functional here, you sum over a lot of sources and a lot of receivers these random IIDs which have mean 0. So what you get in your image is 0. So this and why this happens? Okay, this happens because this, as I said, this noise is uncorrelated. So this is the key word. If you deal with uncorrelated noise, then Kirchhoff migration is the best thing you can do. And in fact, I think that from the statistical point of view, there is a paper by Jocelyn Garnier and Knut Sol now where they showed that this is the best that you can do. Now, of course, this is not what happens in real life, at least not all the times. Here we consider that the noise comes from wave propagating in a random medium, and here the noise is very complicated. So it's certainly colored, so certainly you have correlations, and it's not so easy to have a model for the noise, okay, because it comes from the wave propagating in the random medium. And that's why your method, adding entries, does not lead to a good image, because these entries do not cancel, right? They are not uncorrelated anymore. Okay, so let me give you a small idea of why this works like that. So I will consider first just a point scatterer located in this point y star z star in a homogeneous medium. And then for this scatterer in the homogeneous medium, I will go and I compute the local cosine transform of the response matrix, and then I will look at the singular values. Now, if somebody here knows, if I didn't consider the local cosine transform but the Fourier transform, that for one small target I will only get one singular value that is significant, and the corresponding singular vector would be exponential I omega over C naught, the travel the distance between the point and the receiver, okay? So this is in the Fourier transform. Here, because we use the cosine transform, we get two singular values, and the corresponding singular vectors are like that. So here I simplified. If these are orthogonal, then this is true. So we get the cosine and the sine, and both of them contain the information that we need in order to locate the object. Now, what will happen in the layered medium? So around the time that the coherent, that the echoes from the object that we wish to image arrive, this is what we observe. So this is a decomposition. We say this is a model. We say that the data decompose into the coherent part, and the coherent part is the one that goes from the source, doesn't see the random medium, goes directly to the object and then comes back. This is what we call the coherent field. And then we have the incoherent field, and this one is the one that contains all the reflections of the waves with a random medium. And then, okay, so this is what we get at the window that contains the echoes from the object. What do we get in the previous windows? So in the previous windows, we only get incoherence, because the coherent field did not yet arrive. We just get the reflections from the random medium. And now here I put a reference to a book where, first of all, this can be found, but many other things. So this is a book by Jean-Pierre Fouque, Jocelyn Garnier, George Papanikolaou, and Knut Scholl, now on wave propagation and time reversal in random layered media. So this is a very good reference for this subject. Now, I want to have a model for the coherent field. So if this was just in a homogeneous medium, my response matrix would just be the integral over omega of omega square f cut, and instead of this g ODA, I will just have a g0, which would be the Green's function, okay, from the source to my point, and then back from this point to the receiver. Now, in the layered medium, the ODA theory, the Odor-Diansky theory, says that the Green's function is replaced by this one, the ODA Green's function, or this is a way of writing it, which is just what you had in the medium times this term, which is a small random arrival time shift. So I say it's small because it is of the order of the pulse width, and then you have the ODA kernel. And now the ODA kernel is a Gaussian kernel that is written here, and what is important is just to look at this Gaussian. So you have this pulse spreading. So the pulse is spreading as it propagates into the medium. And the spreading depends on the frequency. So the higher the frequency, the more the spreading. And here appears the localization length, which is the scale of exponential decays of the coherent part of the wave. So we have basically the Green's function that we had before multiplied by this Gaussian. And what this tells us is that if I fix the distance that I go in the medium, then as frequency increases, the amplitude of this Gaussian decreases. So only the lower frequencies can penetrate deep enough into the random medium in order to see the object. The other ones do not arrive there. Okay, so this is what I saw. Only lower frequencies can penetrate. So just to show this in a picture, I take now so this matrix is not observable, right? I cannot get it on the array, but this is a model. So if I have this matrix, if I could record this matrix, then I could do the singular value decomposition, and this is what I would get. So you see, instead of having something that is constant over the frequency, what I get is something that is exponentially decay. And if you remember in my data, I told you to remember that I had a plot where my first singular value was doing exactly that. So I can only observe this part, which is the coherent part, for the lower part of the frequencies. Okay, so then what happens to the rest? The rest is the noise, and so the response matrix for the noise is a real symmetric Toeplitz matrix. This is due to the fact that the medium is layered, and we can characterize the spectrum of this matrix by its symbol. And there are a lot of things that we can say, but I'm interested here on two. So the first thing that we can explain, that we can show theoretically, is that there is this accumulation of the top singular values. So this means this clustering of the singular values that we were observing for the noisy part of the signal is explained theoretically. And also we can show relations like that. So here, this is important for the detection and the imaging. If I call lambda 1 n the largest singular value of the matrix that corresponds to the noise, and lambda 1 c the largest singular value of the matrix that corresponds to the good part, then I have this relation. What I observe, so lambda 1 is what I observe, the singular value for p. Here it's for the eigenvalues, but it's the same. Okay, so lambda 1 is in between this one and the sum. So basically, I can detect something, an object there, only when lambda 1c is big enough, right? Because if lambda 1c is 0, then this tells me that the object is not seen by the array. Okay, and I want to mention that the analysis of the algorithm in the case of the layered media was done in collaboration with Ricardo Alonso, who is a postdoc with Liliana Borchea at Rice University. Okay, so now I would like to conclude. The proposed filtering approach is general and in fact it does not use any a priori information on the clutter. Of course the analysis was done only in the layered case and I'm not sure that we can do it in the general case for any random media. We are currently working on testing, on generalizing this algorithm to the case of multiple targets. So if you have more than one, can you really see them in the medium, etc. Thank you for your attention.
Very nice talk. Questions? Yes?
One of my colleagues who works on landmine detection was following the live streamed lecture, and so he just asked me to check that it would work as well for electromagnetics.
Yes, I don't see any reason that this will not work for electromagnetics, but I think that the proofs will be much more elaborate.
Yes?
Well, I'm asking a very ill-informed question, but I mean, your technique of dividing the thing up into 2s and then 4s and then 8s, and then using cosine transforms, sort of reminds me of wavelet analysis.
Yes.
And also of the Weil transform.
Yes.
And I was wondering if what you're doing could be expressed in those terms.
Okay, we did the local cosine transform. I think we could have done the wavelet transform, but this is maybe easier to analyze theoretically. I don't know. I think that it could work with another time frequency analysis, and we don't really need to use the cosine transform, if this is your question.
Yeah, well, I mean, the Weil transform takes data in one variable and transforms its data in phase space.
Yes.
So you can analyze both the
Both
spatial
at the same
variation and the frequency variation simultaneously.
Okay.
Of course, you have to, well, there is the question of doing some sort of convolution to smooth it out, which is often done with Gaussian wave packets, as you do.
Okay.
So there may be some connection. I mean, I'm not an expert in this at all, but it does strike me as having some superficial similarities anyway.
Okay. Thank you. I will look into that. I'm not sure that it is connected. Probably.
Any other question? So what happens if there's significant multiple scattering between your targets?
I think this is a hard case, yes. You mean if I have more than one target and then there is multiple scattering in between them?
Right.
In fact, I can always detect, I hope, with the numerical examples that we have tried, we can always detect the one that is stronger. So there is always someone that is stronger if it's closer to the array, for example. And then for the one that it is in the back, it's not obvious that, it's so easy to detect it. And maybe you have to take into account, at least at the analysis, the multiple scattering. So there is an interplay between the multiple scattering between the two targets and the single scattering, the multiple scattering between the background and the... So it's not so obvious that it goes through, but it should go through if the multiple scattering between the two objects does not overwhelm the single scattering from the second object. Is this, I think this is what we, or at least at this situation, I think that this will work. I don't know in the others. Otherwise, we can try to remove from the data also this multiple scattering. But then we need a model, and it's not so obvious that you can remove it in a general case.
Right, any other questions? That closes our afternoon session and this workshop. We'd like to, well, first of all, save a little more applause for our tireless organizers, Lassie, Malcolm, Slava, who set a bad example this afternoon, Gunther, Hiroshi. Thank you very much for your hard work and for bringing us all together.